Dear students, in today's class, we shall discuss the development of the algorithms or the direct methods. Okay, so we shall discuss this Gauss elimination method, that how it works. So stepwise, we shall develop the algorithm, and we shall write one pseudocode. Okay, so there are two methods that is part of. Actually, these are not exactly in the syllabus, and in the previous batches, there used to be one CFD lab. So in the CFD lab, I used to conduct this coding things also, and we used to discuss these algorithms. But since the CFD lab is not there, actually, this by some programming language, the students, if you know Fortran, if you know C, whatever the language is, you know, you write first, you understand the algorithm. I think many of right. So you must do a programming for Gauss elimination. It will give you very good confidence and very good understanding of the direct methods. So let us start the algorithm. Okay. So very quickly, I just make a review, very quick review. Just I show the previous classes things. These things, this note, it is not with you guys right now. So I shall send you tomorrow. So these are the direct Cfd L method we have shown, and we have told that these are the stationary iterative methods, where we just shift all the quantities in the right hand side except the diagonal term. So coefficient of Scarborough condition, that is a necessary condition. But not a sufficient, maybe satisfied, this may not be one more thing is that whatever the derivation, whatever the discussion we made in the previous class, that was based on the Laplace or Poisson's equation, this equation, and then you solve the matrix. So very important point is that when you are using Gauss elimination, Gauss-Seidel, Jacobi, you should not worry, because then by that time you are only handling the algebraic equations. So you need not worry about whether the differential equation was for heat transfer or the equation was for fluid flow. It does not matter. So my point is precisely that whether you are solving the continuity equation or the x momentum equation or the energy equation, it does not matter. When you discretize it, you get a matrix, and then you simply solve this matrix. Okay, so here we are showing it for the Laplace equation. So it can be continuity equation for pressure, it can be x momentum equation for u velocity. In all cases, you get linear differential, means linear algebraic equations or linearized algebraic equations with maybe more number of coefficients. Okay, so it means that whatever the equation solvers we discuss, that is not valid only for this Laplace equation. Those are valid universally. Those are valid for any equation. Okay, those are valid in one dimension, those are valid in two dimensions, those are valid in three dimensions. This you have to understand. Okay, so since this is an elliptic partial differential equation, this is easy to handle, and we have to definitely use the implicit method. Because of that, we have started showing with respect to this Laplace equation, but it can be any other equation. It can be an unsteady state problem also. Okay, so let us first I discuss this Gauss elimination algorithm, and then we shall point out some more things. Okay, so here I have told you, in the direct methods there is no concept of convergence. In direct method, we get solutions in single step, and we take that if our calculation steps are correct, whatever the solutions we are getting, those are like accurate solutions, exact solutions. But truly, you cannot get any exact solution in computer programming. Okay, so what is happening that in Gauss elimination or any direct method, we tell that whatever the result we are getting, they are by definitely converging. So this concept of convergence does not exist in Gauss elimination because in direct methods there is no initial guess. So the methods where we need an initial guess and keep on improving upon the initial guess, in that case we need one convergence. Okay, so it is iterative method where we repeatedly invert the matrix. So using equation solver means equivalent the steps we perform, they are equivalent to inverting the matrix and taking a matrix vector product. So inverted matrix and the right hand side vector, their product will give you the unknown vector. Okay, so it means that whatever the methods we are using effectively or unknowingly, we are actually taking in computational language matrix vector product is sometimes written as matrix vector product, sometimes written as matrix vector product. So this is the station. We decide the diagonal term. I have told you many times, I may ask in the exam also, the point where you are writing the equation, at that point, whatever the term you have, so you are writing this equation at point ij. So nodal value is tij. The coefficient of this nodal value is alpha. So alpha must be on the diagonal term. Okay. So for this equation, alpha is in the diagonal term. Remaining terms will be either in super diagonal or in sub diagonal. Okay. So if there is any term other than temperature, it will come to the right side. Okay. So you know that the basis is that all the unknown terms in the left hand side, all the known terms in the right hand side. So that is just for remembering it. So we have discussed, we have just reviewed the iterative method of the previous class. So we have this convergence criteria. So we can define an error in different ways. Okay, global error or local error. So when you are going for direct methods, there is no concept of error. There is no concept of convergence. Okay. And then we have just highlighted some differences between the direct and iterative methods. And you remember, whenever you are going for CFD, more than for 99% problems or more than 99% problems, we are going for the iterative methods. So whenever we are going for CFD, you take it granted that mostly it will be iterative method. Sometimes in special cases, people may use direct method because your matrix will be huge. Your matrix will be very large. CFD means you are solving matrices, square matrices, and they will be very large. Okay, so they can be of size million by million. People are using in turbulent flow million by million sizes. Okay, so those kind of matrices, how will you handle in direct methods? You have to go for the iterative methods. Invariably, you have to use iterative methods. That is all about we have discussed in the last Friday's class. So in today's class, let us start the direct methods. So I have told you that all the direct methods, they stem from the Gauss elimination method. But Gauss elimination method itself is prone to the round of error. So because of that, when you have a large matrix or you have large number of equations, then you have many calculations to perform in every step. So number of calculations are more. It means the computer is performing more and more, more approximations and accumulation of more errors. Okay. So round of error will contaminate your solutions. More number of divisions, more number of multiplications. So because of this round of error will be contaminating the Gauss elimination results, because in Gauss elimination, the operation count is of the order of n cube by 3. So this is a big number. So this n is the size of the square matrix. So when your matrix size becomes larger, this n cube becomes a very big number. So n cube by number. So by operation count, we mean that from the starting up to the ending, how many additions, divisions, subtraction, and multiplication operations you have performed, an estimation, not the precise number, but an estimation of those operations. So more number of operations, it means it is not desirable. Okay. So in Gauss elimination, we get lots of a huge number of operation count. Okay. So Gauss elimination is suffering from the round of error problem, and we don't use Gauss elimination in actual CFD problem where we are going to solve for large matrices. Okay, so then one direct method or direct equation solver, that is for Cramer's rule. So we have just shown it already that for 3 by 3 matrices you can use it very efficiently, but when you are going for bigger matrices it becomes impossible to implement. Okay, so because this operation count grows as factorial of n plus 1. So n is the size of the matrix, so n plus 1. When you increase n from 3 to 4, 4 to 5, or 5 to 6, so when you go to 10, then it becomes factorial 11, and factorial 11 will be a huge number. Okay, so if you take Gauss elimination, it will be 11 cubed by 3. So 11 cubed by 3 will be something around how much? It will be around 10 cube, suppose. So 10 cube means uh, 1000. Huh? So if 10 cube is 1000, and if you take factorial 11, so factorial 11 will be a very big number, much more than this. It means that this Cramer's rule we should not use in CFD or even for our any problem. Okay, and then for a special kind of matrix, when the matrix is tri-diagonal, tri means 3. So when use Thomas algorithm, and in this case, this is an improved version of Gauss elimination for a specific shape of the matrices. If it is a banded matrix with the lowest possibility, so lowest possible banded matrix will be of bandwidth 3. So that is tri-diagonal matrices. So when we are solving this tri-diagonal matrix system, then we use Thomas algorithm or tri-diagonal matrix algorithm. So this is sometimes known as TDMA. So for TDMA, the operation count is low, so it is of order n. Now, just for your information, this tridiagonal matrices, when do we get? So when we are solving one-dimensional problems, okay? So one-dimensional problems, when you are using lower order schemes, okay, basic differentiation schemes, then one-dimensional problems, they give us tridiagonal matrices. So if you are using two dimensions, if we are solving this Laplace equation in 2 dimensions, you get a pentadiagonal matrix. So pentadiagonal matrix is reduced to 2 tridiagonal matrices in 2 different directions, and they are solved by Thomas algorithm in sequence, in step, once in x direction, once in y direction. So these kind of things are known as. So we shall discuss these things. These are when we discuss the line by line method, maybe in tomorrow's class, we may discuss this line by line method. Okay. So whatever this, one more thing is that when we discuss this Gauss elimination, means Gauss Seidel and Jacobi method, we are talking about the point by point method. So we are moving from one node to another node. Okay. So now let us directly come to the Gauss elimination. So we have given the background. So what we are doing in Gauss elimination, what we shall solve here, we shall not discuss the cases where pivoting is required. Okay. So in fluid dynamics, I have told you before that by default, more or less number of times, your matrix is diagonal dominant. It means that if you are using a central differencing for the diffusion term, and if you are using central differencing for the pressure gradient term, and if you are using backward differencing or upwinding for the convective term, your matrix will be diagonal dominant. So you remember what I am telling. I have told you in Navier-Stokes equations or in any full governing differential equation, we can have maximum 4 types of terms: unsteady term, convection term, diffusion term, and the source term. So for example, if you consider the Navier-Stokes equations, this unsteady term, you can use backward difference or you can use forward difference. We have already discussed FTCS, BTCS things. The diffusion term, the term with viscosity or the term with the Laplacian, by default you have to go for the central difference. When you are going the pressure difference, pressure gradient, then we have to use the we have to go for the central differencing. And when you are using this upon this convective term in the left hand side or the advective term, you don't have any choice other than backward differencing. So backward differencing is known as upwinding scheme when you talk about the fluid flow. So you have to take backward differencing at least of second order. So this backward differencing of first order, this will give something known as false diffusion or numerical diffusion. or it will generate some artificial viscosity or numerical viscosity that will again contaminate your solutions. Okay, so if you are following this guideline, that upwinding for the convective term, central difference for pressure gradient and viscous terms, then your matrix will be diagonal dominant for the fluid flow equations. Okay, so generally in fluid dynamics problems we don't go for pivoting. By pivoting we mean that we our diagonal term, it will be the largest term in magnitude in one particular equation. So in one particular equation there are n terms. If you have an n by n matrix, so you have n terms or n coefficients. Now diagonal dominance ensures that the modulus of the diagonal term, it is greater than the modulus of all the remaining terms added up. Okay, so if it is not happening, then we do some swapping. Okay, by some swapping, we make the matrices diagonal dominant, and then we, after making it diagonally dominant, then we use the Gauss elimination. So why do we need the diagonal dominance? Because in direct methods like Gauss elimination, even in Thomas algorithm, every time we divide, there are steps where we divide by the diagonal term. So when you are dividing by the diagonal term, this diagonal term should not be very small. It is impossible that it is zero. Simply it cannot be zero, and it cannot be close to zero. So terms like 0.002 will be considered as zero. So if in your diagonal you are having terms like 0.0002, actually it is zero. And when you keep on using this data, you are actually dividing by zero. And dividing by zero means your program will stop and it will give you none. Okay, so it means that your in your calculation of Gauss elimination, there are steps where you divide by the diagonal term. So if the diagonal term is A11 or A22 or AKK, you are dividing in every equation with the AKK term. So AKK cannot be zero, AKK cannot be a small number. Okay, so that is ensured by the swapping of the rows. Okay, so then we can get the pivoting. We say it is pivoting, and then we solve. Then we use Gauss elimination. So we shall use two straight lines. With respect to two straight lines, we shall explain how to develop the algorithm of Gauss elimination, and then you will easily understand and you can remember it for whole life. I don't think you will forget it. Okay, so let us consider. So let us first discuss this. Graphically, we are showing the algorithm that we have a sparse matrix. It need not be sparse. It can be a dense matrix. It can be a sparse matrix. So after implementing the discretization, after all these steps, you are coming here. You are getting Ax equals to B system, where A is the matrix of the known terms. So in a linear equation system, this A is not a function of X. So your unknowns are here, the nodal unknowns are here. This is the unknown vector. This is the right hand side vector with respect to this generated by the boundary conditions and the source term. And this is the coefficient matrix. It is not important. It has to be symmetric or it has to be asymmetric. It does not matter. So when you are using Gauss elimination, there is no kind of requirement whether the matrix is symmetric or asymmetric. So this is a generalized method. It can be used for symmetric method or for asymmetric methods. Okay. Then we perform elementary row operations. So we say in Gauss elimination we perform row reductions. Elementary row operations are also known as row reductions. Then we convert this matrix in upper triangular form. Okay, so this becomes an upper triangular matrix such that most of the terms in this matrix, they change. Okay, and accordingly the right hand side vector, almost all of the terms except one term, it will become vector b to an updated vector or corrected vector b dash, and the original coefficient matrix A, it will be updated to a new coefficient matrix A dash. So now if you look into this matrix system, it is very easy to solve. You can calculate from the back side. Okay. So how is this vector written? It is written as x1, x2, x3, x4 up to xn. So in the last row, in this particular matrix, you have only one diagonal term. So in the last row, there is only one term. That term is A1, B-2, B-3, up to B-n. So this is the vector B. So in this a n last term is b dash n. So here it is b dash like small a dash n x n equals to b dash n. So one equation, one unknown, you can easily calculate x n. When you go to the just last before equation or n minus 1th equation, then you have two unknowns, xn and xn minus 1. But xn you have just calculated here. So xn minus 1 you can calculate. In this way, when you are moving upward, you can find your unknowns starting from xn to xn minus 1 to xn minus 2, like that to x2 and finally to x1. So we shall show how it works. So let us consider two straight lines. Okay, so two straight lines that intersect at a particular point. So when you are finding the equation solver, the solution of any set of equations, actually we are finding the coordinate of the point where all these solutions, all these lines or planes are intersecting. Okay, so actually we are trying to find out what is the precise point of intersection of these straight lines. So that is known as the solution of the equations. Okay, so let us consider two straight lines. These are the two straight lines that have one unique solution. So these straight lines are not parallel, they are not skew, they are intersecting straight lines. So it means that these two straight lines, they must be linearly independent. So a11x1 plus a12x2 equals to b1, and a21x1 plus a22x2 equals to b2. These are the two equations. Okay, and from these two equations we can get the coefficient matrix, and we have this unknown vector x1 x2 and the right hand side known vector. So without pivoting, when we implement the Gauss elimination, then we assume that in this equation this is diagonal, this is greater than this, and here also this is greater than this. So this is diagonal dominant matrix. So the strategy is that in Gauss elimination, we don't do anything with the first equation. Without pivoting, I am discussing, okay? So this first equation, this is kept as it is. And then we modify the second equation. So we do something so that the second equation updates and we get only one equation from one unknown. The same thing we want to generate. So this is the 2 by 2 matrix. This is n by n matrix. This has become upper triangular matrix. So if n becomes 2, okay, if n becomes 2, then this same matrix we can analyze, we can consider this matrix with n equals to 2, it becomes this matrix. And when it is upper triangular, it means that this A21 will be 0. If A21 will be 0, then you can get an upper triangular matrix and upper triangular matrix. Then A21 0 means A22 will be modified and B2 will also be modified. Okay, and then you can solve for x2 and easily for x1. So what we do, it means that, just 1 minute, some phone call has come. Okay, so what we have to do, we have to do something so that from this second equation, we have only one term in this diagonal term. Okay, so what we are doing, we are just multiplying. So this equation will be updated. So equation 2, we shall make it equation 3, such that we shall multiply. We have to eliminate this A21. Okay, so we shall multiply this equation with A11 and the first equation with A21. So if we want to remove this term from the second equation, so what we are doing here, this second equation is multiplied with the coefficient of the diagonal term in the first equation. So A11 is the coefficient of the diagonal term in the first equation. With A11, we are multiplying equation 2. A11 is multiplied is being used with equation 2, and A21 is used for equation 1 for multiplication, and then we subtract this modified equation, this equation, okay, modified first equation from the modified second equation. So that we are doing here. Second equation multiplied with A11 it gives us these terms, okay? And first equation multiplied with a21, this equation you get. Now the coefficients of x1, they are same, okay? So a1121, a1121. So we can subtract it, and then we are left with only one unknown in this equation, equation 3. That is the replacement of equation 2. So this equation, when we write, we take x2 outside. These coefficients we are having as a11, a22 minus a21, a12, whatever we are getting here, and right hand side terms are subtracted like that, substituted like that. So this is our new equation 3, where equivalent to equation 2, where we have one unknown in one equation. So if we find out x2 from here, easily from here, you can find out x1. So here we have to do some, here we shall develop this algorithm. So this entire coefficient term, this we can think that this is some kind of correction term. So coefficient of x2 is a22, okay? So this x2 in the original equation, its coefficient is a2. So it means that this new coefficient is now corrected a22. So it is a22 dash, okay? So we can say that this is a22, this is a22 plus some correction term. So a22 dash. So this is a22 dash into x2, and right hand side was b2. So this is some correction over b2. So this is b2 dash, okay? So now this equation 3, we can read it as a22 dash x2 equals to b2 dash, where all these terms are known terms. These are known terms. You can easily calculate x2 by putting the value of x2 here. You can find out x1. So for two equations, it is easy to explain, okay? Now a22 dash x2, the meaning is like that. A22 dash x2 equals to a22 plus a correction factor, and b2 dash equals to b2 plus correction factor. So we want to write this a22 dash as a22 plus correction. So to do that, if we divide both the sides with a11, here with a22, we want to write this equation in this format, a22 plus correction, okay? So if we divide the both sides of equation 3 with the coefficient of a22, then we shall get this arrangement, okay? So we are dividing both sides with the a11. So we are left with a22 minus a21, a12 by a11, okay? This term, when you divide by a11, then you are getting it as original term plus correction, okay, into x2, the unknown, equals to original right hand side of second equation plus the correction term. This is the correction term. So you can see here that we are dividing by the diagonal term, okay? This is the diagonal term. So when you are dividing by diagonal term, it must not be 0, or it must not be close to 0. Because of that, you have to do pivoting if pivoting is not done. So when you are using central difference scheme for this convective term, and if you don't follow some guidelines, you get some wrong solutions or physically meaningless solutions. So central difference scheme will give you unstable solutions or meaningless solutions if your grid is not very fine, okay? So for these convective terms, we don't use the central differencing scheme. If we want to use the central differencing scheme, we have to satisfy one condition on cell Peclet number or cell Reynolds number, okay? If we don't do that, then these numbers may become absurd, okay? So now what we are getting with this rearrangement, we can arrange these equations as a11x1. So original set of equations, now they can be written as a11x1 plus a12, means this is the first equation and this is the second equation. So if we write in the matrix form, so this will give you an upper triangular matrix, and it is easy to solve. So what is happening that you have a 2 by 2 matrix. So for a 2 by 2 matrix, there is only one forward reduction. So what we have done here, that multiplication coefficients and then subtracting and then getting a modified equation, this step is known as forward reduction, okay? So if you have a 2 by 2 matrix, you have to modify only the second equation. You need not touch the first equation. It means that For a 2 by 2 matrix or for two equations, you need only one forward reduction. Okay, so we are having only one forward reduction and we are getting this equation, modified equation, which is solvable. It means that when we have such kind of n by n matrices, for n by n matrix to get an upper triangular matrix, we have to make n minus 1 forward reduction. So for 2 by 2 matrix, we are having 2 minus 1 equals to 1 forward reduction. So it means that if you have an n by n matrix, you should have n minus 1 forward reduction. With n minus 1 forward reduction, with every forward reduction, one row, it will fall in this fashion, in this style. So after n minus 1 forward reduction, your total matrix will be upper triangular. Okay, so that point we are discussing here. Okay, now we just develop the algorithm, so it will be very easy to understand from here. So this is very important comment statement which I have written here. Okay, now let us generalize it. So this is for 2 by 2 matrix. We want to connect it to n by n matrix. So we want to write this 1 1 1 2 etc terms with terms of the generic indices I, j and k. Okay, how the k is coming here we shall show here. Now let us come to this correction term. So a22 dash equals to a22 plus correction. So here we are showing the correction. This term we are writing here. Okay, and from here we shall generalize it. So a22 dash equals to updated term. Okay, updated term equals to original term plus correction. So original term, we always write the matrix terms as aij. Okay, so we say that the matrix is aij xj equals to bi. The matrix equation, when we write this equation, so we write this is aij, this is xj, and this is bi. So terms of the matrices, these are denoted by the symbol small a subscript small I small j, where I is the index for row and j is the index for column. This is very important. You must remember it. Okay. So here we have the terms. Now it means that this is the original term. This is aij. So I is 2 and j is 2. So if it is aij, so it means that the left hand side terms, this must also be a dash ij. So if it is a dash ij, it is a dash ij. This will also be some kind of ij. Okay, so there will be only I and j as free index. Okay, this you have to understand. So this is not tensor thing, but if you understand tensor, it will be very easy to understand and remember. So you know that I am repeating what I am telling. This is aij. So this is one term and this is another term. So this is the correction term. So this, if it is aij, output, this is output term. This must be a dash ij, and this will also be aij, means some kind of term, and ij. If there is any other index, that will come as a dummy index. Okay. So if it is ij, then we can tell that I is 2. This is I, so I is 2, and this is j, so j is 2. So wherever there is 2, one of them will be I and another one will be left with j. So this is I, this is j, this is I, this is j. So if it is I, then this is j. So now after putting the values of I and j, we are left with a dash ij equals to aij minus ai1, a1j, a11. Now what is this 1? Okay, so this is for the second equation. So when you are going for the second equation, we are performing the first forward reduction. So we need one index for the forward reduction. Okay, so it means that when we are going from this matrix to this matrix, we cannot do it in one step. We have to follow n minus 1 forward reduction. So how will you write these forward reductions? You will tell this is my first forward reduction. After the first forward reduction, your second equation, this off diagonal term, this lower diagonal term will be 0. Sub diagonal term will be 0. Then you go for the second forward reduction. With the second forward reduction, the first two terms of the third equation or the third row. So every row represents terms of an equation. Okay, you know that this row corresponds to first equation, this row corresponds to the second equation. So every row corresponds to an equation. So the first forward reduction, your first off diagonal term is gone. If you have more terms in a second operation, your first two terms from the third equation, they will be gone. Like that, when you go for n minus 1 operations, only the diagonal term in the last equation, it will be left. All other terms will be made 0. And these right side terms, these terms, not right side, the remaining terms in the matrix, they will be updated. So it means that, so forward the reduction, it will have an index, an integer. So the index will vary from 1 to 2 to 3 up to n minus 1. This is the understanding. So when you are getting this term, so this means that that particular index was 1. So the forward reduction index was 1, and whatever this index is there, that is actually the index for the forward reduction. So this 1 here, this is the index for forward reduction. This is the point, and this you have to understand. Okay, so this index is denoted by the symbol k. Okay, so for the second equation, your k is 1. For the third equation, k will be 2. So now if we generalize it, we can write that for any equation, your updated term or modified term a dash ij equals to akj by akk. So this is the backbone of the Gauss elimination method for this forward reduction. Okay, so this is happening when k is varying from the first step to the n minus 1th step for the last equation. So for the second equation or second row up to the last equation or the last row, when we are having, if you look into this matrix structure, so what is happening that we are making the terms. So this is one. This is 2 about these terms which are left to the diagonal. Okay, so if we are going for the second equation, we need, so when we are dealing with this, not think second about the first equation. We need a first, we got only 2 equations, they are already done. So it means that our objective is that if our position is here, we shall do forward reduction only for these terms. Only for these terms. So these previous terms, they are not important. This is the understanding. So accordingly, we change the indices for rows and columns. So number of in rows, I, the rows on which we have to operate, they change from k plus 1 to 1, and the columns, they change from k plus 1 to 1. Okay, so these terms I and j, you need, I was from 1 to n, you have n rows and n columns. Okay, but you need not change all the rows and all the columns when you have started it already. So depending on the operation count, means operation index, forward reduction index k, you will choose your this lower limit of this row index and lower limit of the column index. But the upper limit of the row and upper limit of the column, they are fixed, because you have to go to the last row, and for every row you have to edit the last column. Because of that, this is the index for row, and this is the index for the column, and this is k plus 1, this is k plus 1. This means that you are actually dealing with a square block, okay, or square submatrix in this matrix itself by changing I and j. Okay, so I shall show one example. This will be very much clear to you. Now, you have your indices k for the forward operation. You have to deal with how many rows you are dealing with. So if you want to understand it more, we can discuss it again. Okay, so if you have only one equation to edit, okay, then what is happening, your k is only 1. So if your k is only 1, this is the only term which you have to change. So your I will be from 2 to 2. For a 2 by 2 matrix, n is 2. Your n is 2. So if your k is 1 for single operation, this will be 1 plus 1, 2. So 2 to 2. This is not the is 2 symbol. This is the range of the variable. from k plus 1 to n. Now when n is 2 and k is 1, the number of row becomes 2. Okay, so this is I equals to 2, and when j equals to also becomes 1 plus 1 to 2, so j becomes also 2. So I and j both become 2. So you have to deal only with this 2 term, with this term. This is the understanding. Okay, for 2 by 2 matrix, this choice, it is telling that you deal only with this term. You can also make it from I equals to 1 to n, and j equals, means I equals to 1 to n and j equals to 2 to n, from second equation to the last equation. But it is irrelevant. Okay, these terms, certain those terms will have no role. Actually, terms outside the diagonal, these terms will have no role actually. Okay, so this is the algorithm. Then we write these steps in a pseudo code that you can write in a programming language in Fortran or C. So we keep this index outside. So under this k index, we keep on operating on rows and columns. Okay, so you can put I outside or j outside, it does not matter. You can interchange the rows of I and j, but k should be outside. Okay, so your k, the operation, how many reductions are required, so that you have to fix first. So it is outside. So for this particular step, okay, for this particular reduction, for the first reduction, you change the rows from k plus 1 to nth row. So from the k plus 1th row to the last row, and from the k plus 1th column to the last column. Okay, and then whatever we have written here, this is coming here. So this is in computer programming, this statement is known as the assignment statement. You don't take that this is same. So this is not same actually, it is assignment statement. So it is not that this Aij and this Aij is same. So this is old Aij or original Aij, and this will be updated Aij. So this is an assignment statement. What we are doing, you calculate this term, whatever you get as an output, you assign this output to this variable, allocate that value to this variable. Okay, so this step will make it forward reduced matrix. So we are getting this forward reduced matrix after this algorithm. Okay, so this is the half of the algorithm, forward reduction algorithm. Now when we go for the actual programming, what we do that, we convert this matrix to an augmented matrix. Augmented matrix means we convert this square matrix to a rectangular matrix. We take the right hand side matrix and we append this with the square matrix, so we get one extra column. Number of row, it remains same, so we have n rows, but we have one extra column, so it has become now n plus 1th column. Okay, so this is the original matrix, and this is this, suppose this is modified, and this is this augmented matrix. Okay, so you have to find the value of x. So let us consider one 4 by 4 matrix, and let us try to understand whatever we have written here, these things, how it works. Particularly, we have to understand the implication of k. What is k actually? So to understand it, let us come to a simple example where we don't use any value, but just we show the terminologies, and that will make your concept very clear. So let us take one 4 by 4 system. Okay, so we, for a 4 by 4 system, we need 3 steps. So k will be 3. So it means that k will be varying from 1 to 3. So once you have k equals to 1, then you have k equals to 2, and then you have k equals to 3. So what we are doing, this is the original matrix, and this is the appended matrix. So this is the augmented matrix, 4 rows and 5 columns. Okay, so original matrix is here, and then we put here some dotted lines, and then whatever the right hand side you have, you paste it here. So I should have written here B, instead of B1, I should have written it as A15. So this B2 will be A25, and so on. Let us keep it as it is. Okay, now when k equals to 1, we shall operate from the second equation. Okay, for k equals to 1 is for the second equation, and then what we are doing, that our I is changing from k plus 1 to n. Our n is 4. Okay, so number of rows, there are 4 rows, So every row will be modified. Okay. So starting when k is 1, so from second row up to the last row. So second row, third row, last row, all the terms, they will be modified. So A will be A dash, all A's will be A dash, and B will be B dash. So this is for the rows and columns. It is telling that starting from the second column up to this last column, up to this fifth column, all the terms will change. So I was taking that we have a rectangular square submatrix. With the augmented form, we have a rectangular submatrix. So with the k equals to 1 step, this is our step. So our one equation, one diagonal, one off diagonal term, it is made 0. So with k equals to 1, our second equation is reduced. Now when we go for k equals to 2, so we don't touch equations 1 and equations 2, they are already done. So we have to remove this term. In the k equals to 2 step, we have to remove this term. To make it eliminated, okay, what we do? We choose I equals to k plus 1 to n always. Here k is 2, so 3 to 4. So we need to handle only with the third row and the fourth row. And j will be 3 to 5, third column, fourth column, fifth column. So only these 6 terms we have to modify. We are doing it. So it was dash, it has become now double dash. So this second forward reduction is done. Let us come to the third forward reduction. When you go for the third forward reduction, by that time, our first equation, second equation, third equation, they are untouched. They are as they are. And the fourth equation, now double dash has become triple dash. So this term is gone. So when it is removed, then we have an upper triangular matrix. So this is an upper triangular matrix. When k is 3, I is going from 4 to 4. This is 4 to 4, fourth row. And j is going from 4 to 5. So change is the so this is forward reduction. So I think all of you have understood this. Okay. So but I am telling you, you read it 1,000 times, it will not help you if you don't write a program. I am telling you, this is my experience. Without writing a program, if you read it, CFD is not for reading, CFD is for doing. Okay. So you read it, you practice it for exam, but you have to write in a program. Or initially you can use a program, existing program, you run it without understanding, and then you try to understand. That is also okay. So if from internet or from, and then you start try to crack that program or to decode the program from the first few lines, then you move move every subroutine or every do loop. If I say do loop, you try to understand, I think then you can do it. Okay. So programming is required, I am telling you. If you want to really do CFD without programming, it is not possible. Okay. And then here you have this updated matrix form, upper triangular form. Then you have to find out this unknown vector, this vector. So now if you look from the bottom side to the top side, this is the last equation. So here for the last equation, your degree of freedom was x4. Okay. So in this case, you have one equation, x4 is the only unknown. So you are easily getting x4 equals to right hand side by left hand side. So b4 triple dash by a double 4 triple dash. So every time you see that, you are dividing by the diagonal term. Because of that, I am pointing it out, the diagonal term cannot be 0. If it is 0, you have to do swapping to make it non-zero, and that is known as the pivoting. Then you have found x4, then you have to find out x3. To find out x3, you have to come to the n minus 1th equation, or the third equation. So here, what is this equation? This is a33 double dash x3 plus a34 double dash x4 equals to b3 double dash. So x3 you will get b3 double dash minus a34 double dash x4, a34 double dash x4 divided by the diagonal term. Okay, then you can calculate x2 and you can calculate x1. Okay, this You know the value of x4. You can put it, you will find x3. Okay. Now this was for 4 by 4. This is just for illustration. Let us make it for a general matrix, an n by n matrix. Okay. So I shall not take much time, but this is very important that you write a program. So now this upper triangular matrix in the augmented form, we write in the generalized matrix form. Okay. So here the first row will be A11 up to A1n. N is the number of rows, and this is B1. So we could have written it as A1n plus 1. Okay, we can write it as A1n plus 1. Second row, third row, fourth row, this is the diagonal. If you come to the last row, the diagonal term ANN, it has become A dash NN. Okay, this right hand side vector term A dash nth row n plus 1th column. So A dash n plus 1. The matrix size is n by n plus 1, and the unknown vector is xn minus 1, xn minus 2, etc. So this is the nth equation. This is the n minus 1th equation. This is the n minus 2th equation. N minus 1th equation, if you look at how it is looking like, A dash n minus 1 xn minus 1 plus A dash n minus 1 n xn equals to A dash n minus 1 n plus 1. Okay, so let us try to make the algorithm based on this. Just by observation, you can easily do it. So the last equation, we have one unknown, one equation. So what is this equation? This equation is A dash nn xn, A dash nn xn equals to A dash nn plus 1. You know A dash this part, you know this part, one equation, one unknown. So you can easily find it out. We have found it out. Then you come to the previous equation. What is this equation? A dash n minus 1 into x n minus 1. This term plus A dash n minus 1 n xn. A dash n minus 1 n xn equals to this term, right hand side known term. You have written it. So here, only this is your unknown. All the known terms are shifted to the right side. This you have calculated xn, you know it. You are shifting to the right hand side and dividing by the new updated diagonal term. So you get xn minus 1. So it means that you are going for a backward substitution. You found xn, now you got xn minus 1. Ultimately, you want to find out x1. This is very easy. Then you come to this n minus 2th equation. N minus 2th equation, you can easily write it like A dash n minus 2 xn minus 2 plus A dash n minus 2 n minus 1 xn minus 1 plus A dash n minus 2 n xn. How to remember actually? So you just remember the matrix equation is written as Aij xj equals to Bi. If you remember only this thing, you can do any algorithm, I am telling you, this kind of algorithms. So this formula only you have to remember, this form, this equation you have to remember, and you have to understand what is this. By remembering this, you can easily understand that the use of the indices. What is j? X will also have the same index. That is important. And this is the ith equation. Okay? So by looking into this, you can write any equation anytime. So I am coming back here again. Okay, so if you get here, A dash Ij xj, ith equation, n minus 2th equation. First index is n minus 2 everywhere. N minus 2, this is n minus 2, n minus 2, n minus 2. It is j, A dash Ij xj. If it is n minus 2, it must be n minus 2. It cannot be anything. A dash Ij xj, n minus 1, n minus 1, n, n. Okay, and this is the augmented matrix, n plus 1th column, n plus 1. Because this is this column, this is n plus 1th column. So it is very easy to understand. Now, you already know xn, you have just calculated xn minus 1. These are known terms, shift them to the right hand side and divide by the updated diagonal. So this is your generalized form. So there is the summation. Okay, to make the general formula, you cannot do with this because there is no summation here. So here we get a summation of two terms. Okay, because of that, we have to come up to this step, we have to show. We need not go to n minus 3. Okay, this is sufficient. Now, to make the generalization, you put n minus 2 equals to I. Okay. So if you make n minus 2 equals to I, then whatever the terms you have here, like n plus 1, n, and n minus 1, so n minus 2 equals to I, so n equals to I plus 2. Okay. From here you are getting it. This you want to write as xi, aij xj, so that you want to write with respect to I or j. So n minus 2 is I, so this will be xi. So n is I plus 2. So now you have n plus 1. So n plus 1 will be I plus 2 plus 1, I plus 3. N minus 1 means I plus 2 minus 1, so I plus 1. So whatever things we are calculating from here, just put it here. If you put it here, now you get a compact form. So n minus 2 means I, so this is xi, and this is n minus 2 is I, diagonal term, a dash I, n minus 2 is I, n plus 1, it is I plus 3, this term, n minus 2 is I, n is I plus 2, I plus 2, n is I plus 2. So like that, we have these terms. Now, these two terms, they are in the left-hand side. They are having ax, ax. So they have similar kind of nature. We sum them up. Okay. So a dash, this is the right-hand side term. A dash I minus 3. Now, here what is happening? We are getting a dash ij xj. Always you remember this formula. This will help you always. Aij xj. This thing is important. So that thing you can use here again. So aij xj. Okay, aij xj, aij xj. So aij and xj terms you are taking the summation. So summation you are taking from I plus 1 up to I plus 2 here. So you are getting, instead of j, you have already used j. You already have j. So you are using an index k, new index. It can be m and anything. So a dash ik xk, where when k is I plus 1, a dash I plus a dash I plus 1, x I plus 1. When it is I plus 2, a dash I plus 2, x I plus 2. So we have made the generalization. Then again we make it in the final form. Okay. So now we just make it these I terms here. We remove these I terms by the n terms. So whatever things we already had here, I think there we have done some kind of repetition. Instead of introducing this, some steps we could have skipped actually, but you follow it. So then we are finally getting the terms with I and n here. Okay. So this I plus 3 we are writing, instead of j we are getting n plus 1, a dash I, and then we are getting this I plus 2 is n, I plus 2 is n. So this is going here. Okay. So when we are considering all the equations, all the rows, n number of rows, then you are finding x1. Then what we have to do with x1, all the terms, they should go to the right hand side, subtracted from b1. So n will come into the picture. Because of that, the upper limit we are taking to the maximum number of rows in the matrix. Okay. So this term now it is written in the generalized form. This is the generalized form for the back substitution. So we are going from xn up to x1. We are moving up. So when we are moving up, the increment is negative increment. So in the do loop, I is going from n minus 1 in steps of 1, means up to n minus 1 in steps of minus 1 up to 1. Okay. So we can just write the pseudocode that this I, it will change from n minus 1 to 1 in the limit, in the interval of minus 1, and we have this formula xi equals to whatever we have already got, that we have written here. So this is the pseudocode for the back substitution. So in the Gauss elimination program, we have two do loops. If you think, one do loop is for the forward reduction, that do loop is already written here. So this do loop is for forward reduction, for making the matrix upper triangular. Okay. And then we have to go for the back substitution to find the degrees of freedom, unknowns. For that, we shall go for the back calculation or back substitution. So this is the subroutine for that. Okay. Actually, in previous years, in CFD lab, we used to spend 3 hours at a stretch. All the direct methods we used to derive in the blackboard and we used to discuss. Okay. But I suggest you that you do it. You write a program, or if you don't have a program right now, you download it from the internet. You see, you look into this. Okay, and don't get afraid of programming, because if you want to learn CFD, if you want to do well, you cannot avoid programming. Without learning programming, CFD, you cannot master it actually. So CFD is not a subject for reading. If you read it, it will not help you. You have to do it. Okay. Only by doing you will see that lots of things that look simple, they are not actually simple. Okay. So let us stop here today. In tomorrow's class, we shall discuss the derivation of Thomas algorithm. This is simple version of this Gauss elimination, and then we shall solve one problem. Okay. One problem is here. So thank you for this class. Okay. Thank you. I shall share this note tomorrow.